We're going to find the area of the region that lies inside of two curves. R equals the sine of 2 theta and R equals the cosine of 2 theta. We might recognize that each of these is a rose with 4 petals. Because remember, when we have something of the form R equals the sine of n theta, if n is odd, we have n petals, and if n is even, we have 2 n petals. Because our instructions don't include actually graphing this, we're going to go ahead and take advantage of Desmos. We'll graph the first one by typing R equals the sine of parentheses 2 theta. Boy, that's small there. And then the second R equals the cosine of parentheses 2 theta. And then blow it up just a bit here so we can see what the actual curve looks like. Or I should say what the actual curves look like. Now this, of course, doesn't look quite right, so clicking on the wrench here allows us to convert this into a polar grid. Let's go ahead and import that graph here so we have something to look at. And I'll just quickly resize it here. Now we're looking for the area that lies inside both curves. So we want what's inside the blue and simultaneously what's inside the red. In other words, we want the portions where the two curves overlap. Or more accurately, we want the value of the total overlapping area. Notice that there are 8 places where there is overlap, and so we can take advantage of that symmetry. And in fact, there's an internal symmetry in the places where they overlap. So we really only need to consider half of the area of overlap and multiply it by 16. And that makes it pretty nice because then we only have to deal with one curve. In order to determine what curve we're dealing with, we start with we're going to draw a ray that starts at the pole and then straight out. And the first curve that I intersect is the red one. The red one has a maximum value when theta is equal to pi over 4. Looking at our two equations, if theta is equal to pi over 4, the cosine of 2 theta is going to be the cosine of pi over 2, so that's 0. If we look at r equals the sine of 2 theta, if theta is pi over 4, then the argument is pi over 2, and we have r is equal to 1. We can also see it from here, but I don't want to rely on that completely, right? We see the equations that we entered, and the red one must be r equals 2 sine theta, but there was another way to analyze that. So we're looking at that we're going to use f of theta is equal to r times, the sine of 2 theta, but now we have to deal with our limits of integration. For the limits of integration, we need to know where these curves intersect. So we're going to set the sine of 2 theta equal to the cosine of 2 theta. And folks, for our picture right now, we're looking at quadrant 1. These two expressions will be equal to each other if 2 theta is equal to pi over 4. That's where the sine and cosine match. Therefore, theta must be pi over 8. So for the red curve, in this black shaded area here, we're looking at theta going from 0 to pi over 8. So that helps us set up our integral. Our area is then equal to, remember we were going to use 16 of the little segments that we found. So 16 times 1/2 of the integral from 0 to pi over 8 of the sine squared of 2 theta d theta. Applying a power reducing formula and simplifying the arithmetic in front of the integral, we're going to end up with 4 times the integral from 0 to pi over 8 of 1 minus the cosine of 4 theta d theta. Remember, we double the angle every time we use a power reducing formula. This will, of course, integrate to 4 times the quantity of theta minus 1/4 times the sine of 4 theta, evaluated from 0 to pi over 8. Putting 0 in place of either of these thetas is going to give us 0. And so we end up with 4 times pi over 8 minus 1/4 of the sine of pi over 2, which is of course 1. Our final answer is that the area is equal to pi over 2 minus 1. Quick little mental work. Pi over 2 is bigger than 1, so pi over 2 minus 1 is positive. It must be because we did find area after all.